Welcome to this explainer. I am so thrilled to have you here today because we're about to decode something that is absolutely vital to modern industry, yet kind of completely invisible to most people. You know, when you look at an industrial plant, a massive refinery, or a huge manufacturing facility, it's really easy to just think of those miles and miles of steel piping as static, rigid, unchanging structures. But actually, that couldn't be further from the truth. Industrial piping systems are dynamic, breathing monsters. They expand with blistering heat, they contract with freezing cold, and they are constantly under massive internal pressure. So today, we are going to explore the fascinating engineering components that keep these metallic beasts from just tearing themselves apart, expansion joints. Okay, let's dive into this. Here is our roadmap for today. First, the high stakes of piping. Second, basics of expansion joints. Third, controlling pressure and movement. Fourth, varieties of expansion joints. And finally, number 5, protecting delicate equipment. All right, kicking things off with Section 1, the high stakes of piping. To really grasp why these components require such exactness, we kind of have to look at what happens when that engineering fails. Like I mentioned, piping is not just static metal. It's a highly dynamic system, carrying volatile substances under immense stress. And sadly, the history of engineering is often written in tragedy. When we talk about thermal expansion and pressure, we aren't just talking about abstract physics on a chalkboard. We are talking about forces that, if left unchecked, literally have the power to level entire facilities. The 1974 Flixborough disaster really stands as the ultimate, grim reminder of these extreme stakes. Let's look a bit closer at the facts from our source material. In 1974, a chemical plant in the UK suffered a massive explosion that tragically killed 28 workers and caused widespread devastation. The cause? A catastrophic failure of a temporary 20-inch bypass line. Now, what's really critical for our understanding today is exactly why it failed. The line utilized expansion joints to accommodate movement, and the joints themselves actually did what they were supposed to do. They flexed, but they failed spectacularly because the system lacked adequate structural restraint. The immense internal pressure twisted those flexible joints until the pipes literally tore open. It's a sobering horror story that proves expansion joints, without proper disciplined control, are a recipe for absolute disaster. Moving right along to Section 2, Basics of Expansion Joints. Keeping that sobering reality in mind, how do we actually solve this? I mean, how do we give a rigid steel pipe the ability to grow and shrink with temperature changes without it just bursting at the seams? Well, that brings us to the fundamental purpose of the expansion joint. And I want to ask you exactly what's written here. What size mechanical hard pipe loop would provide the same flexibility as this compact joint? Look at that massive, looping bend of pipe. That's a traditional way engineers absorb thermal growth. The pipe literally just bends. Now compare that to the compact joint outlined in red. That small, corrugated metal bellows can absorb the exact same amount of thermal movement as that giant loop, all while taking up a fraction of the space. It's an incredible achievement in space-saving efficiency and flexibility. But as the Flixborough disaster taught us, that flexibility comes with a massive catch. Let's read this quote from our source material together. In exchange for providing the most freedom, this joint requires special care in overall design. This right here is the central paradox of our entire explainer. By giving pipes the freedom to move thermally through these flexible bellows, we are fundamentally weakening the pipe's ability to hold its own shape under pressure. Giving it freedom demands absolute, rigorous control over the forces inside it. So, the crucial point is, how do we exert that control? Section 3, controlling pressure and movement. To do that, we first have to understand the invisible enemies here, pressure thrust and squirm. Just imagine blowing up a long, skinny balloon. As the pressure builds, the joint doesn't just get wider, it wants to elongate, and eventually it dangerously buckles and snakes out of shape. That is squirm. Pressure thrust is that immense axial force constantly trying to blow the pipe apart. But that's not all. Engineers also have to fight torsion, which are those twisting forces, and cycle life fatigue from the constant repetitive flexing over the years. If the piping isn't strictly guided and anchored down, these combined forces will absolutely destroy the system. And this brilliantly illustrates the solution. Notice the heavy main anchors at the corners. These are robust, structural lockdowns that literally absorb that massive pressure thrust load so the flexible joint doesn't have to. Then look along the straight run of the pipe at the pipe guides. These guides don't stop the pipe from moving, but they force the thermal expansion to move in a perfectly straight, predictable line into the expansion joint, completely eliminating the risk of squirm and torsion. The anchors lock it down, the guides keep it straight.
Let's look at how we apply this. Section 4, Varieties of Expansion Joints. Now that we know how to anchor and guide a system, we can start getting creative. Because industrial layouts are incredibly complex, engineers have developed specialized expansion joints to solve very specific spatial and physical problems. First up is the baseline, the single untied expansion joint. It's really just the corrugated bellows welded between two pipes. It is the simplest assembly, and mechanically, it offers maximum freedom in all 6 degrees of motion. But remember our paradox? Because it has total freedom, it has zero internal means to contain pressure thrust, and it is highly sensitive to twisting torsion. Therefore, using this joint means you have to rely entirely on those heavy external main anchors and guides we just talked about. But what if you can't build massive external anchors in your facility? That's where the single-tied expansion joint comes in. Notice the tie rods running right across the joint. Engineers have brilliantly integrated external restraint directly onto the assembly itself. These tie rods act as limits, containing the pressure thrust so the piping system doesn't have to bear the full load. Now, what's really interesting about this slide is how we handle angular movement. Engineers use hinge joints for single-plane bending, or the more advanced gimbal expansion joint seen here. It kind of looks a bit like a mechanical puzzle, right? It uses 2 perpendicular hinges connected across a central ring. Unlike the single joints that absorb straight-lined push and pull, this articulated joint actually prevents straight axial movement, but allows bending about both axes perpendicular to the pipe. When you pair these gimbal joints with pipe guides, you can force thermal motion to travel along safely controlled angular paths right around corners. It's incredibly clever. And then we have the universal expansion joint. Visually, you can see this is basically an assembly of 2 single joints separated by a spool of pipe. But the secret here is what it lacks. By deliberately removing any anchor on that center spool piece, the entire assembly turns into a flexible linkage. Because the center is free to move, this linkage system converts the bending flexibility of the 2 bellows into massively large transverse or sideways displacements. It's the perfect solution when a pipe needs to shift significantly from side to side rather than just growing longer. And there are other advanced setups too, like pressure balance joints, which perform similar miracles of routing complex force profiles without needing massive main anchors. Bringing it all together now. Section 5, Protecting Delicate Equipment. So we've spent this whole time talking about protecting the pipes themselves, but pipes exist to connect things together. And while thick steel piping is incredibly rugged and tough, the equipment it connects to often is not. Notice the pump at the bottom right. Expansion joints aren't just there to keep pipes from breaking, they are absolutely essential for isolating delicate rotating equipment, like pumps, compressors, and turbines. When hundreds of feet of steel pipe get hot, they expand with the force of a literal freight train. If that growing pipe is rigidly bolted to a pump, it will crush the pump casing, misalign the internal rotors, or shatter the bearings. By incorporating an expansion joint right near the equipment, engineers instantly increase the flexibility of the piping, absorbing that thermal load and even isolating mechanical vibration, which saves the expensive machinery from total destruction. And to put into perspective just how fragile this relationship is, consider this surprising fact from our source. The piping attached to a rotating machine might be restricted to just 5%, yes, 5% of its normal allowable expansion stress limit. The pipe itself could easily survive higher stress. Well, actually, it could survive a lot more, but we have to engineer the system down to a mere 5% tolerance purely to ensure that the pump or turbine it attaches to survives the day. That is an astonishingly tight margin of error. Which brings us to our final thought. We started with the tragedy at Flixborough and journeyed through the incredible hardware that allows modern industry to safely harness massive thermal and pressure forces. It all really boils down to a profound engineering paradox. Freedom requires discipline. If our industrial progress requires our systems to have the freedom to expand, do we have the rigorous discipline, the anchors, the guides, the exact calculations required to control it? It's a fascinating question that mechanical engineers answer every single day. I want to thank you, the Focus Learner, for joining me on this explainer today. Keep exploring, keep questioning, and I'll see you next time.